Hello students, in this lecture we are going to solve some numericals from the chapter Current Electricity. Now we will solve numericals. Let us solve first numerical. A battery of EMF 4 volt and internal resistance 1 ohm is connected in parallel with another battery of EMF 1 volt and internal resistance 1 ohm. The combination is used to send current through an external resistance of 2 ohm. Calculate the current through the external resistance. So, dear students, in this numerical, we got the data from the numerical. So, we need to draw diagram for solving this numerical. A battery of EMF E1 and internal resistance R1 is connected in parallel to a cell of EMF E2 and internal resistance R2. This whole combination is connected to external resistance R. Therefore, we have to find the current, that is I1 plus I2 passing through external resistance. Now, in the data, E1 is equal to 4 volt, R1 is equal to 1 ohm, E2 is equal to 1 volt, R2 is equal to 1 ohm, capital R, that is external resistance, which is equal to 2 ohm, and we have to find the value of I1 plus I2. So, from the given figure, we have to use Kirchoff's voltage law to loop A, B, C, D, E, F, A. We may write minus R inside the bracket I1 plus I2 bracket closed minus I1 R1 plus E1 is equal to 0. Therefore, minus 2 inside the bracket I1 plus I2 minus 1 into I1 plus 4 is equal to 0. Therefore, 3I1 plus 2I2 is equal to 4, equation 1. Similarly, applying Kirchoff's voltage law to loop B, C, D, E, B, we may write the equation minus R inside the bracket I1 plus I2 bracket closed minus I2 R2 plus E2 is equal to 0. Substituting the values, we may write minus 2 inside the bracket I1 plus I2 minus I2 plus 1 is equal to 0. Therefore, 2I1 plus 3I2 is equal to 1, equation 2. These two are simultaneous equation. Therefore, by solving equations 1 and 2 simultaneously, we get the values of I1 and I2. Therefore, I1 is equal to 2 ampere and I2 is equal to minus 1 ampere. Therefore, current through external resistance, which is equal to I1 plus I2, and we will get this current is equal to 1 ampere. We will solve second numerical. A voltmeter has a resistance 30 ohm. What will be its reading when it is connected across a cell of EMF 2 volt having internal resistance 10 ohm? In order to solve this numerical, we have to draw the diagram. In the diagram, voltmeter having resistance RV is connected to a cell of EMF E1 and internal resistance R. Here we have to find the value of V. Now from the numerical we may write the given things. E1 is equal to 2 volt, R is equal to 10 ohm, RV is equal to 30 ohm, and we have to suppose to find the value of V. So by applying Kirchoff's voltage law to the loop ABCDA, we may write minus I into RV minus I into small r plus E is equal to 0. Substituting the values in above equation, we may write minus I into 30 minus I into 10 plus 2 is equal to 0. Therefore, minus 40I is equal to minus 2. Therefore, I is equal to minus 2 upon minus 40. That is, I is equal to 0.05 ampere. Now, V is equal to I into RV. Therefore, V is equal to 0.05 into 30. Therefore, V is equal to 1.5 volt. Now we will solve the next numerical. A potentiometer wire has a length of 1.5 meter and resistance of 10 ohm. It is connected in series with the cell of EMF 4 volt and internal resistance 5 ohm. Calculate the potential drop per centimeter of the wire. From the data given in the numerical, we have to find potential drop per centimeter of the wire. In the data, capital L is equal to 1.5 meter, which is equal to 150 centimeter. Capital R is equal to 10 ohm. Capital E is equal to 4 volt. Small r is equal to 5 ohm. And potential gradient K is equal to V upon L we have to find. We know the formula. I is equal to E upon capital R plus small r. By substituting the values in the above equation, we may write I is equal to 4 upon 10 plus 5. Therefore, I is equal to 4 upon 15 ampere. Now, V is equal to IR. Again, substituting the above values of I is equal to 4 upon 15 ampere and R is equal to 10, we may write V is equal to 40 divided by 15 volt. Therefore, potential gradient K is equal to V upon L, which is equal to 40 divided by 15 upon 150. Therefore, V upon L is equal to 40 upon 15 into 1 upon 150, which is equal to 4 upon 225. Therefore, the potential gradient, that is K is equal to V upon L, is equal to 0.0178 volt per centimeter. The next numerical is when two cells of EMFs E1 and E2 are connected in series so as to assist each other. Their balancing length on the potentiometer is found to be 2.7 meter. When the cells are connected in series so as to oppose each other, the balancing length is found to be 0.3 meter. Compare the EMFs of the two cells. Here, the two cells are to assist each other. That means some method. and the balancing length for the sum method is L1 is equal to 2.7 meter, which is equal to 270 centimeter. The two cells are to oppose each other, therefore they are in difference method, and the length given is 0.3 meter, which is equal to 30 centimeter. Here we have to find the ratio of two EMFs, that is E1 upon E2. By using the formula, E1 upon E2 is equal to L1 plus L2 upon L1 minus L2. By substituting the above values in the given equation, we may write E1 upon E2 is equal to 270 plus 30 upon 270 minus 30. Therefore, E1 upon E2 is equal to 300 upon 240. Therefore, E1 upon E2 is equal to 15 upon 12. Therefore, E1 upon E2 is equal to 1.25. Now, we will start the last numerical of this chapter, that is, the resistance of the potentiometer wire is 8 ohm and its length is 8 meter. A resistance box and a 2-volt battery are connected in series with it. What should be the resistance in the box if it is desired to have potential drop of 1 microvolt per millimeter? Now, the data is small r is equal to 8 ohm, capital L is equal to 8 meter, E is equal to 2 volt, and the potential gradient K is equal to V upon L, but V is given in microvolt, so we have to convert 1 microvolt into volt. Therefore, 1 microvolt is equal to 10 raised to minus 6 volt, as well as 1 millimeter is equal to 10 raised to minus 3 meter. Therefore, the value of K is equal to 10 raised to minus 3 volt per meter. Now, the potential gradient K is given by the formula K is equal to V upon L, which is equal to E upon capital R plus small r into R upon L. Therefore, capital R plus small r is equal to ER upon KL. Rearranging the equation, R is equal to ER upon KL minus R. Therefore, R is equal to inside the bracket E upon KL minus 1 bracket close into small r. Substituting the values in the above equation, we may write capital R is equal to 2 upon 10 raised to minus 3 into 8 minus 1 bracket close into 8. Therefore, R is equal to inside the bracket 2000 upon 8 minus 1 bracket close into 8. Therefore, R is equal to 2000 minus 8. Therefore, R is equal to 1992 ohm. Therefore, the resistance in the resistance box is 1992 ohm. In this way, we have completed the chapter current electricity. Thank you.